There we go. Well, good morning, Nick. Good
Good
morning,
morning.
Bruce. Good morning, anyone who is listening to this recorded. This is the first in a short series of 4 webinars that the Triumphs Initiative is presenting this fall. Today, our presenter is Nick Scoville at Ursinus College. He'll be talking to us about a primary source project that he wrote a couple of years ago. I think before we turn the floor over to him, I wanted to let everybody know. Let's see, I'm going to share my desktop. This is the Triumphs website. All things Triumphs can be accessed through here, in addition to the project that Nick's going to talk about in a couple of minutes. I just wanted to let people know, just to start out with what Triumphs is. The few paragraphs that you see on the page on your screen give a good summary of what we're about. We are trying to prepare classroom materials for teaching undergraduate mathematics, topics across the undergraduate curriculum, including the one that Nick is going to talk to us about now. The initiative has been under an NSF grant, active since 2015, to do this work. I think without further ado, let me unshare, and I'll turn the floor over to Nick.
Great. Thank you, Danny. Thank you, everyone, for tuning in. So I want to tell you a little bit about my project, the closure operation as the foundation of topology, which is a pretty short primary source project. The bulk of it only lasts about 3 or 4 pages, and it's based on some of the writings of Kuratowski, as well as a little bit of the writings of Hausdorff as well. So what I'd like to do is first just maybe explain what the overarching structure of the project is, and especially its goals and its purpose. And then I will go through the project sort of piece by piece, pointing some things out. At the end, I'll talk about how I was able to use this in a class. I've been able to teach with it only once so far. And then finally, I'll give some ideas that I've been having recently about how you can maybe use this project as a jumping off point to do some kind of axiomatic investigations with students like one does in a geometry course, which I don't have this idea fully fleshed out yet, but I think there's some interesting potential there. So I'll talk about that at the end. So this project is based on a paper that Kuratowski wrote, which was based on his doctoral dissertation. So some of you might know the name of Kuratowski from some of his contributions in graph theory, that he has this result about when a graph is planar. But this dissertation of his had to do with some ideas in point set topology. And what he does, at least in the section of the paper that I'm using in this project, is he builds the axioms for a topology using the so-called closure operation. So some of you might know that a topology, as we think of one today, is defined as collections of open sets satisfying certain properties. But what Hausdorff does is he axiomatically defines a closure operation. Says there's this operation you can do to sets. It satisfies some properties. And from there, he shows that this is equivalent to the open set axioms. And so you could build your topology from either point of view. And so one of the things that this exposes the students to is the fact that we work with axiomatic systems in mathematics, that there are multiple axiomatic systems, that there are different viewpoints, and that the axioms you choose can very well determine what kinds of mathematics you're doing. So let me start to go in a little bit of detail on this. I want to share my screen here. I tried this earlier with Danny. Let's see if I can figure this out again. There we are. So I think you're able to see this project, the closure operation as the foundation of topology. So it begins with a short introduction, talking about Kuratowski, who he was, as well as Felix Hausdorff, because we look at some of his writing as well here. So to get to kind of the start of the sort of mathematics of the project, we begin by sharing a quote from Hausdorff, and this is from his 1957 book of set theory, which is actually the third edition of his set theory book. It went through a lot of interesting revisions, and I'll note something interesting, I think, about the difference between the first and the third version. So in this quote from Hausdorff, he's sort of talking about the different ways in which you can axiomatize a topology or do topology. And the axioms he gives here, sort of the standard ones, are the so-called closed sum and intersection axioms, which are pretty close to what we normally use in a coarse and point set topology. And in a coarse and point set topology today, we use the open set axioms. And sometimes you might show that the closed set axioms are equivalent to the open set axioms. That's nice. It's not too surprising, though, for students, I think, once they sort of realize De Morgan's laws, that this should be the case. So here's Hausdorff in his 1957 book version of set theory. The thing that I wanted to mention I think is really interesting is that in the first version of set theory in 1913 or 1914, there's a fourth axiom that Hausdorff lists, which is that if you have any 2 points, then there exists 2 open sets which separate those 2 points. And so today we know that as the Hausdorff property of being a topological space. So Hausdorff originally included it in his definition of a topology. Somewhere between 1913 and 1957, that sort of fell out of vogue. I don't really know why, how, or when, but I think that's really interesting. So Hausdorff mentions the sort of standard set topological axioms here, and then he mentions the closure axioms here. And so he says you can also begin a topology by saying that if you have a set A, there's this thing you can do to A called the closure, which satisfies the following 4 properties. And then he's got this nice sentence here that really drives a lot of what the rest of this project is. It would also be possible to make these properties our starting point, a la Kuratowski, by taking them as our axioms for the set function A closure here. And so as I mentioned in the next sentence, the goal of the project is to prove this last claim made by Hausdorff by following Kuratowski. So this sort of sets the stage, I think, fairly well. The first task that I asked the students to do is to actually prove that these closed sum and intersection axioms are equivalent to the open set intersection axioms. Those are the ones that a student who's taken topology for a week or a couple of weeks will have seen, and it's not too bad to prove this using De Morgan's law. Task 2 says that if you start with the closed set axioms, then you can prove that the closure of A is closed, which makes perfect sense. And one thing that I'm hoping students start to think about here is how certain concepts are defined. So one thing that students might or might not realize, and that I hope this project points out to them, is that under the standard definition of a topology, an open set is an undefined term. There is no meaning to what it means to be an open set other than you're part of this system that satisfies these certain properties. And that's to be contrasted with what we'll see a little bit later, that in the closure axioms, a set is defined to be closed if it's a closure. Like, that's what we mean by something being closed here. So moving from Hausdorff onto Kuratowski, as I mentioned earlier, Kuratowski himself says that the paper we're looking at is a slightly modified version of his 1920 doctoral thesis. And so Kuratowski goes on to say that in his paper, he's going to propose these closure axioms and their consequences, and then show that they are equivalent to the standard axioms. At this point, I say that it's worth pondering exactly what Kuratowski is trying to do, thinking about this axiomatic nature of what he's doing, that if I start with these 4 axioms, then I can build the rest of topology, and I can build, in essence, some theorems. So from those 4 axioms, the first thing that Kuratowski does is he proves these 4 theorems, and as we'll see later, these 4 theorems will help us to actually show that this system is equivalent to the open set axioms here. So there's 4 theorems. We give Kuratowski's proof of the first one, that if A is a subset of B, then the closure respects the subset inclusion. And then we have the students prove the rest of the theorems here. I give a hint, which I think is needed. Sort of the proofs of these aren't clear if you don't sort of have these things sort of in the background. So these, this task and Kuratowski's proof here gives us these 4 theorems, these 4 properties that follow from his axioms. And then from there, we can prove this theorem, which tells us that, well, this closure operation, once again, it behaves very well with respect to arbitrary families of index sets of intersections and unions. And so students can prove that as well. Finally, we move to this line here where Kuratowski, as I mentioned above, says that we're going to define a set to be closed if it's equal to its own closure. And so that's to be distinguished from the way we define closed in the open set axioms. We define something to be closed if its complement is open. And so this is a different way of defining a concept, but ultimately they're going to be the same thing. Finally, let's see, moving on to task 5. Using what you and Chris have shown, prove the claim, right, that his definition of closed set should actually satisfy these closed set axioms. So that's what we're having students prove there. Finally, in task 6, students are ready if they use task 4, and I think parts of task 3, or these theorems up here, they're able to prove that the closure axioms are satisfied if and only if the open set axioms are satisfied. And so that's it. That's the entire project. It's very short. I wrote it to be done within a class period, or maybe a class period plus some homework. And I think that's fairly doable. So I mentioned that I have done this before. The way I was able to use this in class was I actually used it as sort of a non-traditional final exam. So what I had students do was, I think, work through the first 2 tasks as homework, as sort of part of a kind of a take-home portion of an exam, and they brought it to class. And then in class, I had them work on the rest of the tasks in small groups, in randomly assigned groups. And they were able to get this done, I think, within about an hour. And so this is something that is pretty easy to do, again, within, you know, a 60-minute class, 90-minute class. You could sort of do all of this, again, with maybe a little bit of homework. So the other thing I wanted to mention about this is, as I said, something I've been thinking about in terms of how you could use this to do something similar to what people do with a geometry course, or maybe the end of a proofwriting course. So what happens sometimes at the end of a proofwriting course or in a geometry course is the professor will ask students to, they'll say, well, we've been looking at several geometric systems, different systems of geometry, the Fano plane and such, and different finite geometries. I want you to make your own geometric system. Come up with your own geometry axioms. Tell me what the undefined terms are. What are the terms that are being driven by the definitions? Give me a model for your geometry, something that actually satisfies this to show it's not self-contradictory. Show me that the axioms are independent of one another, that if I take away one axiom, then certain things change, and then prove a few rudimentary fundamental results from these axioms that you've come up with. And this is something that I think gets students to think about the nature of axioms and geometry and such. And it's very much modeled after what Hilbert was doing in the early 20th century. So I was thinking you could probably do something, you could use this project as a jumping off point to do something similar for topology. First, you could ask, well, could I do something similar that Kuratowski does for a topology by maybe talking about compact set axioms and maybe having the whole idea of compactness drive the foundations of a topology? Could I come up with some axioms that drive what it means for a set to be compact, which I could then use to define closed, which I could then use to define open, which I could then use to show that I've got an equivalent system to our standard topology? Could I come up with some axioms that give me a completely different kind of thing than a topology? So in geometry, we have students give axioms and they build a system that might not be related to any other kind of geometry that people have studied before. Kuratowski has these axioms and they end up giving you the exact same thing as a standard definition of a topology. Could you give some axioms for something that gives you something that's like a topology but works differently? What would that look like? This seems to be, I think, something really interesting that students could play around with and begin to do certain kinds of research in, come up with these different axioms, see what follows, what kinds of results can I get that are standard topological results, which ones are different. There seems to be a lot of potential there. And this might be something I'll try myself next time I teach topology, so I have a better idea than this kind of vague thing that I'm talking about now. But I think it's an idea worth pursuing if anyone ever has the inclination to do so. So I think that's basically all I wanted to say about this project. I don't know if there are any questions that people might have or anything else that I could maybe address.
Yeah, sure. I wanted to acknowledge Brian and welcome to the webinar.
Hi, Brian.
Thanks.
Brian, do you or Bruce have questions for Nick? Bruce, we can't hear you at the moment.
Now you're muted.
Okay,
I think Bruce,
now you can hear him. We can hear you.
I think Bruce is muted now, isn't he?
Now Bruce is muted, yeah. If you would, Bruce, if you would turn off the mute button. No, we still can't hear you. Let's see. Bruce, you could use the chat screen as an alternative if you can't get the audio to work. Yeah, apparently the audio isn't working, Bruce. Sorry.
Yeah. Sorry. Thanks, though.
Well, I would just say I don't really have any questions. I don't get the opportunity to teach topology. So, I mean, I've taught a lot of different things, but I was just kind of interested to see, what it looked like, what you had used it for. I more teach algebra, and so I don't really see, I guess, where that fit in. But it looks like a nice project. I like the idea. I have taught a geometry course, and so that's kind of a neat idea of having the students do their own geometry. And I like the idea of the topology as well as kind of a neat idea.
Thanks, Brian.
Good.
I see Bruce has pulled up the chat.
Yeah, so Bruce,
While Bruce is prepping there, let me ask a question, Nick. You indicate that you've used the project as a kind of final exam for students in a topology course.
yeah.
Does it have other sort of curricular goals in a topology course?
Yeah, so I think the other curricular goals, you can introduce things like closed sets to it. You can introduce things like closure. So this could replace the idea of, in topology, you may have a section on like geometric things, the interior, the boundary, the closure. This could replace that as well. And it's one of the things where, you can do it in a day. So the idea of the closure axioms as an axiom isn't usually something that you do in topology. But that's sort of the place where I would use it for the closure for the idea of the closure.
You mentioned that this is based on Hausdorff's set theory book that went into multiple editions, right?
Well, so I pulled the quote from Hausdorff in his third edition, a quote where he starts to muse on the nature of axioms and the different ways in which you can build a topology. And what I really liked is that he had basically the standard axioms we use, the closed set axioms, they're pretty close to the open ones, right next to Kuratowski's closure axioms. And so he was really making that connection that this is something you can do. You could build a topology either way. And so for me, I thought that was a nice jumping off point to have sort of Hausdorff say, here's something you can do, and then say, okay, let's verify what Hausdorff, the master, says we can do.
Uh-huh.
So that was really the only use of Hausdorff. I didn't use much of his mathematics in this project.
But it is significant that this is a book that went through over 30 years of editing.
Yeah.
And you're using text from the latest edition?
Yeah, so that edition, 1956, 57 was the latest edition.
Mm-hmm.
Interestingly, in his first, and as I mentioned, it went through a lot of revision. It went through major, not just a long time. It went through major revisions from the first to the third. In fact, the first being in the 1914 or 13. This was before Kuratowski's dissertation.
Mm.
So the stuff that I showed didn't even exist at all anywhere in the world when the first edition came out.
Thank you, Bruce.
Oh, great.
So you want to, let's see, Bruce writes, I was reading something involving measure theory recently that mentioned a structure that satisfied both the topological axioms and the axiom of the measurability of a Borel algebra. Could this be one of the extensions, alternate axiom systems students could investigate?
Yeah, that makes perfect sense. So I actually don't recall off the top of my head what the axiom of the measurability of a Borel algebra is, but if I, I sort of remember there's these things from analysis, G deltas and F sigmas, these things may be enclosed under certain intersections. So you could easily add this to your topological axioms. So I've got my 3 axioms that a topological space needs to satisfy, that the sets need to satisfy. And then I could furthermore require that the only things that satisfy this are maybe G deltas or F sigmas, or only certain kinds of sets can be built from this. So that would limit the kinds of sets that are in my topology. And then what? I don't know. I think that's exactly the kind of thing, though, that I'm thinking about, where you add something new, or maybe you take something away or put something else in there. So that's exactly the kind of thing that I'm thinking about.
So you really do expect your students to think axiomatically, right? And that's the kind of training that you're giving them through this project?
Yeah, that's right. This provides something that really is there, at least in the history of topology. It really was built very axiomatically and thought of axiomatically, and we still do it pretty axiomatically, but not to the extent that we do in geometry. Like, we really harp on the axioms in geometry and talk about we're only using the axioms, what's going to follow from the axioms. And we do the same thing in topology, except we don't talk about it as much and put it out there as much. And so I think this project gives an opportunity to do that, and a jumping off point for someone who would want to try doing that.
Okay. Other questions? Bruce, are you working on anything else in chat for us? Oh, he's fine. Okay.
So what's the level of the students that you usually do this with? Like, are they, where are they in the program? And you said, would this be, you used to do that as a final exam? I mean, do you see using it earlier in the semester or anything like that?
Yeah, so for the students who are taking a course in topology that I'm teaching, they've taken a course in proofwriting, so they know about things like sets and partitions and equivalence relations and such. And when I used it only once, as I was only able to use this once so far in class, and I use it as a final because I thought that it was unique enough in terms of what it did, but still, or as part of the final, I should say, it was unique enough in terms of what it did, but close enough to the things that they'd seen before, so that it's not coming out completely out of left field. That being said, though, I do think this could be done very early in a course in point set topology. Mm-hmm. So you could introduce the open set axioms, do a few things with them, and then move into this almost immediately. With a little bit of rearranging of things, or a little bit of maybe changing some of the language that I've put in the project, you could even do this on the first day, I think, because it is axiomatic. Now, the students might not really know why you're coming up with these axioms or why you're doing what you're doing, but they don't know what you're really doing, what you're doing when you are doing point set, when you're doing the open set axioms anyway. So if you're the kind of person who likes to start with the axioms in a course in point set topology, you could just as easily start with this, I think.
And then one kind of follow up to that, I guess, but it's unrelated, is, so you said you did randomly assign groups for the final exam. I mean, so yeah. I'm just kind of curious about the details of that. Did you, they just got the same grade? Was there like a distribution of credit for how they graded it, things like that?
Sure. The final exam, it was in multiple parts. So I don't know if I gave part of it as I gave part of the exam as an individual take home. I had them do some stuff individually in class. And then when it came to the groups, it was something like maybe 20% of the individual's final grade was whatever they got, whatever their group earned on that portion of the final. So each group turned in one sheet for that portion.
Okay.
And then it was just integrated in there.
I mean, I think that's useful. I like seeing people kind of if we try to do group work in class, and it's kind of like the perspective the team-based learning people take on it, that if you're in class doing a lot of work together, then that should be part of how they're graded. They should be graded together, right? And so I think it's neat to see that.
Yeah, I agree completely, and I do this often. In fact, I'm doing multivariable calculus now, and every day they are working on 3 or 4 problems together in randomly assigned groups, and they turn in one sheet, and it's graded for the whole group. So I'm a big believer in not only group work, forced groups, but also giving them grades for it, having them, having it count and mean something for them.
Yeah. Thanks.
Yeah, I just want to read Bruce's follow-up here. He says, I took a course in grad school in combinatorial geometry 50 years ago that used closure operators with an additional axiom to generalize the idea of base in linear algebra. It's a very interesting way of looking at a mathematical structure through the lattice of its subsets.
That's really cool. I don't know combinatorial geometry. Yeah, that's really interesting. Okay. I'd love to take a course in that.
Well, thank you, Nick. Thank you, Bruce and Brian. Bruce, would you like to share something else? You trying? Looks like he's typing. Yeah. While he's doing that, I'll mention that the Triumphs group is planning 3 other webinars in the coming days. Here, let me check my schedule. Our next webinar will be Monday late in the day at 5 p.m. Eastern, where Ken Monks will present a project that he's written on Euler's calculation of the sum of the reciprocals of the squares, which is a project that was designed for use in a calculus course. Subsequent webinars will take place next Friday, the 11th, also in the afternoon, and the following Monday, the 14th. So if you're interested in participating in some of those webinars, we welcome your participation in this Zoom room. Anyway, thanks, Bruce. Thanks, Brian. And thank you very much, Nick.
Thank you. My pleasure.
Any last words for our listeners? Okay. All right. Well, thanks for presenting your project. And we'll be back in a couple of days.
All right.
Thanks, Jeff.
Bye-bye.
Bye-bye.